Today I want to study the generality, but I have learned nearly around the curvature, so I want to start from the chapter 3 about curvature in Carrol's space-time geometry. So if you want to know more details, you can check Carrol's book. Okay, let's start. Chapter 3, curvature. 1.3, overview. We all what curvature means, at least information. In the first two chapters, we have felt free to refer to the complex curvature with limits carefully. Clear curvature depends on some factors with the different geometry. But it's not immediately clear how we should attribute curvature to ray. As we have seen, even the metric flat space can look arbitrarily complicated or extravagant coordinates. As is often the case, it really requires quite a bit of care to formalize our institution about the concept into usable mathematical structure. Formalizing what we think is the subject of this chapter. The technique we're about to develop absolutely crucial to the subject. It's safe to say that there is a high density of useful formula per page. In this chapter than in any other. Let's quickly summarize the most important round to provide a roadmap for the formalized program. On the right, in which curvature manifests its real connection, which gives a rectangle space. This unique connection we can construct from the metric I is encapsulated with a cross symbol given by a sigma crucified symbol, the mu sigma, and to this sigma mu delta sigma z mu. I think this is the first type symbol. So I almost forget. Further, I think this type crucifier also exists. But I forget detail. So you can check by yourself. The notation makes gamma lambda mu nu looks like a tensor, but in fact it's not. It's not tensor. Of course, I think. This is why we call it an object or a symbol. Object, we call the fundamental useful connection to take a covariant derivative. To generation partial derivative, the covariant derivative vector field v mu is given by v mu delta mu v mu gamma mu mu sigma v sigma. I think you may know already. So, and geodesic curve geodesic equation is also shown in this part. And finally, we get curvature, Riemann tensor connection by. So I don't know well this curvature, so I want to know in this chapter. Okay, let's go to two covariant derivative. In addition, it became clear that there were various notions we could different function multiple set of tensors. Other concepts such as polymer over a region of the length of some additional piece of structure, namely the intermetric. It would be natural to think of the notion as something dependent exclusively on the metric. In a more careful hardware, we find that curvature depends on the connection, and connection may or may not depend on the metric. But we will also show how the existence of metric implies the unique function whose curvature may be thought of that this is the connection used in generality. So, in this particular context, it's legitimate to think of curvature as characterized metric with a degree. The connection becomes necessary when we attempt to address the problem with a partial derivative not being a good tensor operator. What we would like is a correct derivative, that is, an operator that reduces to zero with initial coordinate but transformed as a tensor on an arbitrary manifold. It's conventional to spend a certain amount of time multiplicating the interest. But in fact, the equation such as delta mu t mu must be generated to cover space somehow. So let's agree that correct derivative would be a good thing to have and go about setting it up. In flat space, inertial coordinates the partial derivative is mapped from KL tensor field to KL plus tensor field, which is linear with a Leibniz root on tensor. All of this continues to be true in more general situation. We would like to cross about the map. Partial derivative depends on the coordinate system. We would therefore like to define covariant derivative operator to perform the function with partial derivative in right rather than simply postulate the answer. Let's motivate it by thinking carefully about the property of the partial derivative should have mathematical after human beings not found lying on sidewalk. We begin by recalling the data map from KL tensor to KL plus tensor, which has these two property: linearity, delta t plus c and delta t plus delta s, Leibniz rule, ts tensor, delta t and s plus t and delta s. No. If delta is going to obey the Leibniz, it can also be written as a partial derivative plus some linear transformation. Yeah, plus some. Yes. There is to take the correct derivative. We first take the partial derivative and then apply a correction to make the result covariant. We are going to prove this ism soundings. See, well, if you are interested. Let's consider what this means for the derivative for vector. It means that for its the covariant derivative d mu will be given by a partial delta plus correction multiplied by set of matrice delta mu plus gamma mu rho sigma. Where n times n matrix where in the dimensionality of the manifold for each mu. In fact, the parentheses are used dropped. Parentheses are used dropped, and whereas this material known as correction coefficients with half-fads in expressment as sometimes we denote this by this rho mu. We therefore have delta mu v mu, delta mu v mu, gamma mu, mu lambda v lambda. Notice that in the second one, the index originator has moved to the second term index original on Broy has moved to the gamma and a new index sum over. This expression for correct derivative of vector in terms of partial derivative. We should be able to determine the different gamma mu lambda by demanding the left side. There is, we want the transformation law to be we want to hope, we want to need delta mu dash v mu dash transform like tensor. So what mean like this, and mu dash delta x mu delta mu v mu. So let's look at the left side first. We can extend it using then transform the parts we understand. Using simple and theory, what is everything we need, and so and how really I understand now your tactics. Okay. This is this is an expression, and delta x mu dash delta mu v mu we use chain rule about partial delta x mu. So delta x mu and delta mu and and delta x mu dash v mu delta x mu dash delta x mu mu dash ram dash lambda. The last part is we don't care. We don't know the transformation rule of gamma, so I leave it as is. And on the other side, we can also expand. Right, we can also expand delta x1 delta mu. Right hand side, we can also expand. So this is a rule. So so the last two equations to be equated. The first time is and therefore cancel. Yeah, these parts cancel. So we rate where I want to go. Where did it go? So mu lambda dash dx dash lambda lambda where we so of course we finally get this relation. So now we get the transformation rule of gamma Christoffel symbol. So so we have changed the index from this equation must be true for any vector program. So we can admit on both sides that the in prime coordinate may be isolated by multiplying by delta or events. The result, lim dash a so delta x mu delta x mu dash delta x dash delta x lambda delta mu delta x mu dash gamma mu like tensor, but not tensor because the second term is not proportional Christoffel's component lambda lambda dash delta this is not true for the tensor trapezoid of the second term on the right probably okay because the correction coefficients are not the component of the tensor. Correction coefficients are not the components of the tensor. Their purpose for a construct will be non-tensor, but in such way the combination 3.5 transfers the tensor, the extra term in the transformation of the pressure gamma is cancelled. This is why we are not so careful in the expression of the correction coefficient. They are not a tensor, and therefore you should try not to lower their index. We are not so careful. About What about the covariant derivative or the sorts of tensor? Similar reasoning to the use of the covariant derivative run from also can be expressed as partial. Omega mu, lambda omega mu, something we could write lambda mu. This is a covariant derivative. We should lower in this because these are four duals of vector. Pay attention to where or other birth. It's straightforward to derive the transform property must be the same of the since otherwise the transform as a tensor, but otherwise is not. So we need to introduce two new properties that we'd like our covariant derivative in addition to commute with contraction. Delta T mu. What transport? Well, what is this? I don't know this relation. Relative partial difference on scalar. Delta mu phi equal delta mu phi. There's no way to derive this property. We are simply given they be true as a part of the differential property. No, the property C is equivalent to saying that chronic delta. No, the property is covariant constant. Delta mu this is such a reason things to ask. This is equivalent, and so delta mu delta rho sigma. Delta mu rho sigma. So なんだこれデルタミューシグナルデルタ T TT rho what is this? I don't know, but I know this. I think this is a basement. This is a basement on logic to create other tensor, gamma or covariant variable is applied to. So applied to for arbitrary phi scalar. Scalar. Let's see. This is. Let's see what the new property imply. Give some round form field omega mu or vector field v mu. We can take the scalar field by to get. I may skip this part because I imagine the reason. So if we want to know the details, you should check the book Carrol. So blah 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 blah. So you express gamma. You express gamma and gamma v omega and this is a scalar. So we use this assumption. So theta mu omega lambda v lambda covariant derivative act on scalar as normal partial derivatives. So you can write like this. So this is true. Is cancel each other. So this is true. I think this part is equal, so this part cancel. So we know the Christopher symbol for transformation of one form, gamma mu lambda equal gamma sigma mu lambda. This is minus part here. We are gamma lambda and gamma lambda So the two extra conditions we have imposed therefore allow us to expose the derivative over one form using the same conditional coefficient we used for. But now with a minus sign, gamma mu delta mu gamma lambda mu nu. So it should come as no surprise according to equal to the infinity to take the covariant derivative of the from it's for its power and it's right. More you should know.これはthis is very I think is a problem, so you can check. D mu 1 bar and gamma mu 1 sigma lambda t lambda mu 2 gamma mu 2 sigma lambda the covariant derivative is covariant derivative this is the general process. You can check it here. It comes from the set lexicon we have it, and the usual recurrence that tensor. So just as comment used for partial semicolon used for covariant. So we denote sigma de and semicolon. This part express covariant derivative with a direction to sigma. So once again in this we stick to we stick to delta sigma. he love the sign in the scope. To define coordinate, then we need to put the connection no matter which is specimen some coordinate system by a set of coefficients. So coefficients number seem to be 64 with me and phi n equal 4, so too many. But I think this would be reduced with thinking symmetry. The name correction improves the fact it used to transport vector to another. As we shall see, it is sometimes used to do the operator and sometimes the coefficients. We could define large number of connection on manifold. This notion. In general, this freedom is not a big concern because it allows the ability to define unique connection, which is one using GR. Let's have the back. The first thing notes the difference of two connection is tensor. But I know already this I skip. This as a classifier as a connection. This is tensor. This is tensor. The cobra. This is tensor. Yeah, of course you know already the transformation rule of gamma in change the coordinate to other coordinate. So let's give a vector V mirror. Yeah, I know. So since V mirror must be tensor as a trivial constant, whether any set of coefficients can be expressed some fiduciary connection plus tensorial connection. Tensorial correction. Next, so you can write gamma plus S tensorial collection, not the connection, correction. It's something like a joke. I don't know. Torsion tensor. Next note that it's complex. We made it from the tensor we can associate with any given correction known at. Yeah. Mu 2 gamma mu. I think this is a torsion part. Torsion part, I think mu. The torsion tensor is clear that torsion is antisymmetric. Antisymmetric is lower in this, so and the connection that is symmetric, torsion free, and the connection torsion free. We can now define the mu by inducing two defined properties. Torsion free gamma mu gamma lambda mu nu. Metric compatibility delta rho z mu. Torsion free. I think this is a very important. Torsion free is according to the metric combat, if the control of the metric with respect to that. This implies a couple of nice property. First, it's easy to show that both lives investment can also zero covariant derivative. Delta rho z mu. Second, meta-combat covariant derivative commit with rising lowering. This for some vector field v lambda. Lines. Low. It's also zero. This matrix. It's an inverse metric oath. Inverse metric. This is an inverse metric. Mu lambda theta log v lambda. First, so Leibniz rule, but one term is there by the above condition compatibility, so that rho the mu lambda v lambda. So delta rho v mu, with non-metric compatible connection, we should have to be very careful about in expressment when taking. Torsion free. One from therefore there is one torsion free connection is compatible with some given metric on the matter. We don't want to make this a part of the dimension covariant depth. They simply single out one of many possible runs. We can demonstrate both existence uniqueness by deriving manifest unique for connection configuring terms. To accomplish this, we expand our metric composite for three different parameters of indices. Delta rho z mu. Existence and uniqueness. Gamma from z. Delta rho z mu nu. Delta rho g mu nu. Gamma rho mu g lambda mu minusでyou can write mu lambda we substitute the second third of this row with the symmetry of the connection delta rho z mu delta mu g mu rho delta mu g rho mu plus 2 gamma rho minus 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 from it's so this for connection 0ロ0 the sigma rho multiple yeah the sigma rho もう the sigma z low delta mu z mu low delta mu low mu delta z this formula is one of the most important ways this commit to it to memory. Of course, we have only purpose and to explain Carrol, it must be of the form. You can check for yes the right answer of that term like transform like question. This connection we have derived from the metric is a one or conversion. It's known by different names. Sometimes Leibniz connection, sometimes the Riemann connection, the associated connection, or sometimes the credible and later. We also sometimes call them credible symbol, but we won't use. So the study manifold with metric, the associated connection is called Riemann. Sometimes should remember with the metric as a Lorentz signature before putting. We should mention some miscellaneous properties. First, note that in order flat the implicit connection we use or critical connection process from the flat method, the coefficient of the in flat vanishes in cut method, but not in curvature. Okay. But consider, for example, the plane in polar coordinates with metric. The non component of the inverse metric readily found to be ZRR 1 Z theta or minus 0. Oh yeah. Notice that we use around we can compute a typical connection coefficient ZRR theta, so suddenly it vanished. But not all then do gamma r shida equal ZR ZR theta of 0, so 2 hours. So continuing to turn the crank, we eventually find something like 4 x0 x total r with 2 parts. From Z is similar. So with Z 8, I think this type Christopher, the number of this is 8. I think and Christopher symbol is symmetry, so only 4 that was reverse. So again, therefore the delta. Counterwise, we even in a curved space. Okay, let's So I have a problem. So let's take a rest.